Patrick joined as well. Good. Right. And Patrick also, thank you. All right. Good. Did you receive, Marcin is also with us. Thank you. Did you receive my email yesterday about some guidelines for preparation of the final project?
Yes, we did.
Yes.
All right. So I think that today you will concentrate just to prepare this project. COMSOL is yours, and I would like, in fact, it would be the best if you could complete the description, final description of the project today, and send it to me. I think it's a good idea. You will have less work at home. If you don't mind, what do you think about such schedule for today classes?
We can try, but I don't think we can do this actually, because you wanted from us some parameters that I think it won't be so easy to find them.
Yes, but I also mentioned in this email that I will discuss with you those guidelines, and we will start, I think, from this. Okay.
I mean, the description you gave us is pretty clear, but the biggest problem with this project is it's very hard to find such publication on different sources of information when we have both a nice picture of porosity and the description of mechanical properties. So not the project is the problem, but the finding information to this project is quite challenging.
Okay, right, but so I will share my screen just for a while, and let us. All right, just a second.
Also, I have a question because last time my project didn't work and I sent it to you and you said that you will go back to me and you did not.
I should do this, but I don't know why I didn't. So just a moment. Right.
Okay.
All right. So you mean that this problem is the most difficult part, yes, of this?
Yes, that's right.
Yes, and even though we found in the publication, sometimes there's lack of a picture that we can use to binarization.
But could you give me more details? What do you mean that there is no pictures for binarization? What do you mean?
So sometimes you have a picture of porosity, but it's not the best picture for binarization because of, I don't know where it is, too much shadow and light, etc., etc.
Yes, but in fact there is thousands or even more papers in the field. So I can't imagine that you can find free papers where those pictures are ready for binarization. So I do not understand really.
So we can take information from one publication and picture from the different.
In fact, it would be the best to use pictures or images from the publication because you have more details about this particular microstructure. However, you didn't find any paper where there is some microstructure of porous materials?
We could, but it's not impossible, but it's very hard to find publication with both information such as about mechanical properties and the nice picture to binarize.
Yes, but why you are talking only about the mechanical properties? I did not mention about mechanical properties of those materials. Did I?
No. I mean, in the project, it's something about tortuosity, something like that.
Yes.
So basically,
but it is not related straight to mechanical properties.
Okay, so maybe I understood it wrong.
In fact, probably those properties of porous materials shall be explained. So let's start from that. All right, because what is porosity? Can you define the porosity now?
The percentage of empty space
according to the
cross section.
Yeah, but if let us assume that we have two-dimensional porous structure. So how can you define the porosity, the parameter called porosity of the material?
By integrating the cross section.
Yes, integration of cross section gives us the total surface. Yes, but as you started, we can also calculate the empty spaces, surface, total empty surface spaces, and divide by the total surface of the material, yes? And it is the porosity. So it is how you can calculate porosity also in COMSOL. Okay?
Okay.
Right. So this is the first parameter. The second one is tortuosity. How it is defined?
I don't really know what it is exactly.
Right. So tortuosity is probably Polish word is more convenient. Krętność. So it means that the total length, when we have not porous material, so the shortest way is just the straight line between 2 points, yes? But in case of porous material, this line can't be very often straight, because on this straight line you have pores, yes? So it means that if the species is moving, is diffusing, so it can't go as shortest way as it is possible, but it has to find some way how to get from point A to point B, and it has to go in such a way to avoid empty spaces, so pores. So in practice, the effective length for diffusion is bigger than the shortest one. And this is just very, very descriptive way of definition of tortuosity. This is this parameter, and the next parameter is just constrictivity. And constrictivity, probably I will share the screen. Right. So if we were here, so again, tortuosity was such a parameter. It is the effective length. In this case, this is the length like here, for example, according to the shortest way. So like this. Sorry. So this is tortuosity. A constrictivity is just because you can imagine, for example, structure like that here the distances between pores are rather similar. However, it could happen that there will be a big pore and small pores, and there is different distance between pores. So very, very small distance and big distances. And this parameter just describes this very short distances in this material, because they very often determine the properties of porous materials. Here it is uniform, rather uniform. However, if the distribution sizes of pores are different, in a consequence, there are also different distances between pores. And sometimes it can happen that on this shortest way, there is such a case that there is only a very thin way where this atom, particle, whatever, diffuses from the left side to the right side. So very often it just determines the properties of porous material. And this is also included in the description of this project here. When we go to the description, you could find here the parameter called tau. It was the tortuosity. It is just what I want that you calculate also this tortuosity based on the calculated effective diffusivity, known diffusivity in solid phase, and known porosity. And this tortuosity can be calculated from here. And following your question that it is difficult to find this, probably this is not precisely written here, but what I would expect that if some of those parameters are available in the literature, in particular a publication from which you have taken those images of porous microstructures, so you can write them. Of course, if you do not have such information, or not all of this information, you should provide only information which was found. This is why you also calculate some parameters of this porous structure. Yes, of course. Yes. Yes. Okay. So it is good time to talk about this today. if you have problem with the topic, okay? All right. So this is why we are discussing on those particular points which are here. So this one should be written if. Is it clear now? So just write, for example, that the authors provided only information about the porosity. Sometimes about porosity and tortuosity. But please provide information which is available in the literature which you have found, okay? Is it clear now?
Yeah, sure.
All right, good. So, but okay, but this is why I recommend to use publication, because sometimes you can find very nice images, but without information, what is the material, method of production, properties of this material. So usually when you find some publication where we have some porous material microstructure, also should be some information about this particular material, or it is a reference in this paper where this information can be found. It is a typical what we do when we use publications. So certainly not everything is in one publications, but there is some references when you can find an extra information, or it is not readily available, and in such a case you will write it down straight, okay? So this is clear now?
I think so.
Okay, good. Probably which so I think that I will comment now point by point what I would expect from you, okay? So the first point is rather trivial, because there is a mistake. Sorry for this, but I presume that you recognize that it is a mistake. So you should send all the information regarding to the project to my address. And what is very important, that you should provide some proper heading for your email. So write group number and put the number of the group, put your surname and first name. This should be provided in the subject field or in your email. You're asked to prepare your project in Microsoft Word format, and also make a PDF file from this document, and both of them should be sent to me. The information which should be provided in the project is the description of at least one and the best 3 porous materials, and each description of the porous material should contain a source, as I written, preferably the publication, and if you download this publication, please also attach this PDF file to this email with the project. Try to find the best 3D microstructures, but of course, for your work with this image analysis, you will use only 2D graphs. So usually when people do 3D analysis, they also provide some 2D cross sections. Okay. Please provide information about what is the material from which this porous material is composed. And as I asked you before, provide the method and description of production of this material. And if available, please send also information which you found about some parameters of these porous materials, like a porosity, tortuosity, constrictivity, and effective diffusivities. And here I will extend this to an extra point, or probably the previous point. Please find definitions in the literature definitions of those parameters. What is this? I don't tell you that there is only one definition, but try to find different definitions. And following this definition, you will go other things. All right. Next, choose one of the porous structures and binarize it. The instructions has been already given to you because you have already done it using ImageJ, and describe in a few steps how you have performed. After that, this binarized file should be vectorized using Inkscape. Also provide in a short description in a few steps how you have done it using this software. The next step will be to put on the same page 3 pictures, 3 images. One is the photo of the original porous microstructure material. Below will be the same picture but after binarization. And the most bottom on the page will be a graph, an image which is the vectorized binarized file.
Isn't the last time the binarized and the vectorized would be the same in our paper?
Sorry?
Aren't the last 2 pictures, the binarized and vectorized, would look the same?
They can be similar, but as you remember, they will be different. Because during
I remember. Sorry.
Vectorization, in fact, there is some rounds are not so sharp.
Yeah, I remember that.
Yeah. Okay.
Can you repeat what type of vectorization we are supposed to use?
What do you mean? What kind?
In the options there are a few types of. There are different types of procedure.
In fact, as I remember, we used standard parameters provided by this program. Okay. However, if you see that those parameters are not enough, such default one, you can just practice and change them and see what is the result. It's absolutely what you can do, but you can try to do this. But if it looks all right with the default parameters, just leave it.
Oh, thank you, I see.
Sorry?
I said I see, thank you.
Okay. Right. So this is this part. And in the 8th point, last time, as I remember, we were just downloaded this vectorized image as a geometry to COMSOL. And you should do this if it is not ready yet. And just do not forget about the change of the dimensions of the object according to my hints which I provided. If you do not remember exactly, of course, I can remind you today as well. But please look into your work whether everything, point by point, you have or something is missing, so we can discuss about this, I would say face-to-face, just discussing about your particular case. And when this geometry is provided with the proper dimensions, the next step will be just the calculation of effective diffusion coefficient. And this should be done according to this guidelines which are provided here. So it means that this is this expression, and we have to calculate average concentration at the boundary. You have to calculate average flux at the boundary. You have to calculate porosity, and all this information should be provided in the table. But the results should be placed in the derived values section in COMSOL, in the project. And when you have all this information here, you can calculate. Yes. 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 Okay, so when okay, so all right, Marceli. So in such a case, when I finish to discuss all the points in the guidelines, please ask this question again, okay? Right. So in this derived values section, you should provide average concentration at the boundary, average flux at the boundary, and there is also possible to calculate effective diffusion coefficient from those two information. And also, of course, the porosity is necessary. Diffusion coefficient in the solid material is just the diffusivity which is provided in this in the equation which is used for calculation. This is just this D. And this tortuosity parameter is defined here. So tortuosity tau is just diffusivity D divided by effective diffusivity multiplied by epsilon, where epsilon is the porosity. So all the data you have when you calculate the average concentration, average flux, and porosity. And it should be done in the direction X, like it is in this project. However, the next task to be done is to change boundary conditions. This, let me go back here, because here the boundary conditions are left boundary, right boundary, and the rest. And this is the case for this column in the table. This column will depend on the reformulated boundary conditions. It means that concentration will be on the top, flux will be on the bottom, and left, right, and others will be no flux. And you will recalculate those average concentration, average flux, porosity of course will be the same, and based on that you will calculate effective diffusion coefficient and tortuosity. And if you have those values for the direction X and direction Y, you can calculate anisotropy as a you can divide the value in direction X by the value of direction Y. And if this coefficient is different than 1, so it means that it is anisotropy. But what is the value? It can be small anisotropy, bigger or very high. So it depends on this value here in this column. All right. It is very important that you send me also, together with this description in Microsoft Word format, also projects done in console. And it can happen that the size of the project after performing calculations will be too big to send it by email. So this is why you have to do the following thing. I mean, go to Study and Clear Solutions. And when it is done, save the project, and its size will be not bigger than 2-3 megabytes, and it is in such a case not a problem to add an attachment to the email.
Could you repeat what should we do to reduce the size?
As it is written in the study 1, press Clear Solutions. Okay. So again, it is here, study 1, and I haven't got Clear Solution now because I have already done it. But when it is not, so we can compute, and after that the solutions will be available and we will be able to clear the solution. Let us wait for a moment. All right, and when it is done, study 1, right click, and we have clear solutions. And after that, save this project, and the saved project can be sent by email to me. Yes, I think in such a case we have finished, yes. Are there any points which are not clear for you?
The points are clear. Sorry to interrupt. I also have a question.
Yes.
So, yeah, it's a quick one. If there's absolutely no parameters in the paper, should we ditch the paper, or is the binarization enough?
You know, if it is very nice structure, just write that there is no parameters, okay, according to the truth.
All right.
Okay?
Okay.
All right.
I have a question about the diffusivity. For the purpose of our simulation, should we always choose the same diffusivity for all of our samples?
You know, from the procedure of calculation of effective diffusivity, you can use the same diffusion coefficient.
Okay.
But in case, but there is one trick here. So if the dimension of our sample is different according to the same diffusion coefficient, yes, because this diffusion coefficient here is quite big, I would say. It is rather for liquid, definitely for liquid. So in such a case, it can happen that sometimes for a very, very small dimensions, time which is necessary to reach a steady state will be much shorter than this one here. Here is milliseconds, so it is rather short time. However, the key point in this project is that this average flux and average concentration at the boundary, it should be calculated when the solution is at steady state. So when it is a steady state, so you have performed calculations. I can't tell you what is the time to obtain the steady state. You have to practice, make numerical experiments. If you add an extra time, let's say 200, and nothing changes, so it is definitely steady state. But if you add 200 and next, and there is a difference between 100 and 200, it means that you can't just treat it as a steady state. Excuse me for a while. All right, so going back, please remember that steady state is necessary to calculate those average concentrations and average fluxes at the boundary. So this is the key point. Probably my recommendation would be that you could prepare such table, for example, for this direction, just for this example here, because in the description they provided all data, and you can just check whether your calculations are correct. They do not provide information, such numbers, particularly here in these derived values, but I told you last time how to do this. So what they have done, they only calculated the integral which gave them the porosity. However, here you provided also information about the average flux and average concentration at the right boundary. So please use this project, this effective diffusivity, and based on those recommendations here, just fill this part of the table and make sure that the values which you obtained, are in agreement with this instruction for the project here. If the obtained values are the same as in the description, so you can be sure that your way or how to do this is correct. Okay, shall we just start from this? Yes, but Marceli, please repeat your question again, because it is I would say it's too general. It is too okay, because it is not. Yes, share your screen, please. Yes. Yes, but sorry, Marceli, can't you use this project effective diffusivities, this one, and just because your project will be different just in geometry only. So please show me what is unclear for you, okay? We have time. All right. But please put your hand on if you are successfully logged on a remote desktop, okay?
Okay, but I've got a problem because number 7, which I usually use, is turned off probably because it.
Number 7, yes.
Yes, and that's why I log into computer 15. But I don't know if somebody other uses it usually. Because number 7 is probably turned off because it is wrote that it was last seen online yesterday.
All right.
And it's impossible to put the pin down. So if somebody uses computer number 15 usually, so tell me and I will try to log on other one.
Does anybody else use or trying to use computer number 15? If not, I think you can use it.
So, meanwhile, can I have a question?
Yes, please.
So I wanted to ask, because you mentioned that it would be nice to send our projects until our today class is finished. So,
yes.
but I'm pretty sure that I won't be able to do this because I need to search for another materials because.
Okay. You know,
so,
it is not obligatory, Eva,
okay.
and to all of you. It is absolutely not obligatory. However, if you can do this, you will have less work to do at home.
Yes, I understand.
It's just my way of thinking, and of course you have time to 20th of June, and
Okay.
it's absolutely okay when you do this in this time.
Okay, thank you very much.
You're welcome.
Can you remind me the name of the tool used in ImageJ to binarize? Is it binarize simply,
yes,
or
just two different possibilities. One is threshold, and another one. Let me find.
Oh yeah, I was looking.
Where is ImageJ? It's here. And the picture. What is this? What is this? I don't know. Someone like this. Yeah. So here you have, I think, just our process is like binary, make binary. One of the possibility. And another possibility is just to use threshold. But at first you have to make this graph as a 8-bit graph, for example, and repeat. Oh no. Yes. Probably something like that. And some filters. Why not? Something like this.
All right, thank you.
You are welcome. Yes. But what was the computer number you used? And it is now switched off? Show me your screen, please. Yes, I see myself, yes. All right. Okay. All right. All right. Okay. Please give me a second, okay? I'll make a phone. All right. In a few minutes, I think the computer should be switched on, and I will ask you to log in again. Okay, Marceli? And also computer 7. So yes.
Great. Great that computer number 7 also will be switched on.
Hopefully, yes. All right. I see only a few hands up. What's wrong with the others? You are not successful, or you have forgotten to put your hand up? Marceli is waiting. What about Marcin? What about Patrick? What about Sylvia?
I mean, why were we putting hands? I'm logged in. Yeah. Okay. So I forgot to put my hand up.
All right. Good.
So I was doing my project and.
Okay. Forgotten. All right. What about Sylvia? Sylvia, are you with us?
Yes, I am. Today I don't have access to a computer, so
all right.
I don't see
okay.
the point, or just log in and don't do anything.
It's a pity. Yeah. All right. So, you know, those who are logged in, you can do your project. I would strongly recommend to start just to fill it, this column for this particular geometry, and compare it with the results in the project description. Okay, let's start from this. Marceli, we are waiting for your computer and also for the second one. But all right. In the meantime, probably where is the what is not clear, because the description how to do this is here. Yes. Oh, you can't see my screen. All right. So
yes, we can't.
Okay. So this is to calculate effective diffusion coefficient. You have to know C out and average, and to do this, here is the definition of an average, and we have done it last time. So what is, Marceli, not clear here, or this is clear? It's not clear. Yes. Oh. Okay. All right, but so
in the meantime, can I have a question about this table in the project?
About the table?
Yes.
Just a moment.
Of course.
Hello? Są włączone. Dobrze, ja oddzwonię za momencik, dobrze? Please try to log into computer number 7 and 1, okay? Just now to let me know.
Computer number 7 works.
Okay, good. Thank you, Małgorzata. Sorry, it's still connected. So let us wait for a while, okay?
Okay, so maybe a coffee break, and then we will go back to do what Marceli wants.
Sorry, could you? So you want a coffee break now, or?
Okay, now let's maybe let's talk about what Marceli wants, and then a little coffee break.
Okay, it can be even longer coffee break if you want. Marceli, are you successful or not yet? So you are logged in now, yes? Okay, so give me a second and run console, please. All right. Działa, panie Jakubie, bardzo dziękuję. Dziękuję. All right, so run your project and show me. Yes. Yes. So try to step by step to find values for the table. Yes. So that's all right. Okay. So what is the close put the console project as an active window. Okay. All right. Thank you. And now you have open component 1. We have some definitions here. All right. So let me press left boundary. All right. Okay. Just a moment. Right boundary. All right. Average 1. All right. Average 1. Okay. It's definitely wrong here because sorry, this is average. Okay, this is correct. Sorry for this, because I have to magnify your screen because I can't see it well. All right. So average operator is operator which gives us an average value at the boundary. So if you show me the instructions for this effective diffusivity, okay? No. I don't know whether this is previous. However, the description in English, which is provided by with the project effective diffusivity. Should be, yes, but you share your screen, so yes, this, I think this one. All right, and let us go one page down. One page down. All right, stay here. You have an average here, and the operator on an average, generally average, is 1 divided by L0 integral, and what is here Km multiplied by C minus C1. This is the thing of which we calculate an average value. In this particular, this means K multiplied the difference of concentration is the flux. If you go on one page down, you have also this C out, which is also an average concentration. This time, this average operator is again 1 divided by L0 integral from 0 to I can't see properly what is there, L0, and this time we calculate average from concentration C. Is it clear? No, not equation, it's just the definition. And in COMSOL, this 1 divided by L0 integral from 0 to L0. This is the operator called average. And when we put after that as C, so it will be an average from concentration. If we put page up, please. If we put Km multiplied by C minus C1, it will give us an average flux. So, look. Yeah, of course. Let's go back to COMSOL. Let's go back to COMSOL. All right, and go to variables 2. And as you can see, we have a defined values called flux average, which is just this average operator, AVEOP1. And this operator is from Kf multiplied by C. And it is the flux. And please put down here below cons or concentration, CON, concentration, underscore alpha AVG. Okay, and as an expression, copy the expression from yes, copy this one, and remove Kf multiply. Leave only C in the bracket. Okay, and this will be an average concentration in description. Write average concentration in description, okay? Okay. Concentration. Okay, good. Right. So this is done. All right. Let me we need also the dimensions of our sample. It means that please magnify this graphics window in such a case that we will see the upper right boundary. Upper right, yeah, yes, even, yeah, it's okay. So now we know that the dimension is, the height is almost 2 micrometers, yes, and the length is something like 2.5 micrometers, yes. All right, so 2 multiplied by 2.5, so this total surface is approximately 5 micrometers square, yes. So let's put it as a variables as well. Let's call this S underscore tot underscore tot of total, and it is 2.5 multiplied by 2. Put it together in bracket, and in the square bracket, square bracket. No. It was, the bracket was correct, but after this bracket, put a square bracket. Okay, and place micrometer, it means UM, yes, and square. So this hat and 2. All right, and enter. All right. So this is in the description, let's call it total surface. All right.
Why our unit changed for meters square?
Because console usually does calculation in SI units. So
okay,
every unit is transformed to SI unit. Okay?
Okay, thank you.
You're welcome. All right. So we have such information here. Good. Now let us go to study 1. Study 1. Okay, and press compute. Sorry, I can't hear you. You know, it's okay now. Right. Let's choose time in the settings, 2D plot group settings, to just start from, let's say 90. It's correct. All right, and press plot. Okay, and now press this arrow, right arrow near the plot. Yes, press. In fact, I can't see any difference on the graph, so I think that this 100 microsecond, I think is okay. All right. So it is steady state. Yes, you can, of course, and plot again. All right. So now it's time to provide these derived values. So right click to derived values. Before you do this, click to surface integration. All right. And you have to change selection to matrix. All right. And evaluate now. Sorry. Before you do this, just in the window table 1 to the right, use this yes, this one to remove it. Near the bin there is, yes, delete table, but to the right. Oh, okay. And now evaluate again. All right. So as you can see, of course, it does not depend on time, and this is just the surface of your sample. So you can.
Shouldn't we change the expression?
Sorry.
Shouldn't we change the expression?
Yes, we definitely should change it. You're right. And as an expression, we should write 1 divided by, instead of 0.8, this micrometer square, remove this, please. 1 divided by and s tot. All right, and remove the table again and evaluate. All right, and this is the in fact now the porosity of our sample. Do you understand why? All right. So in fact, what it is done here? This surface integration. So I will share my screen for a while, okay? All right. So if you want to calculate porosity, so this porosity is called, I think, epsilon. You can't see? All right. All right. And now? Okay. So if epsilon is porosity, so porosity is defined as surface of pores divided by surface total, where surface total is the whole samples together with pores, yes? And S pores is the surface of pores, as it is here. Just a moment. And the surface of pores, it can be calculated as an integral from sorry, it's not exactly what I wanted. It is here. This is this integral, but calculated from 1, and here is this area. Okay. So if we integrate constant function 1 through this porous area, so this porous area will be given like that. And of course, if you want to put it here, divided by S dot, because S dot is constant, we can just, so it's like TS, and here, just a moment, TS. And because this is constant, we can put it here. And this is our expression, which is in COMSOL. 1 divided by S dot. Is it clear now? Okay, good. So let's go back to your project. Share your screen, please. All right. So this is what we really obtain is this porosity. So it is.
Actually, can I have a question?
Yes.
Because the integral that we used here is this integral over not the porosity but over the matrix, the sample. So in description, isn't it should be called 1 minus porosity?
1 minus porosity.
Yeah, because the integral that we are making here is not over the porosity, but is over the material.
Yes, you are right. We do not have to change the formula at all, but it is enough that we subtract this value from 1. It is exactly the same, because the total pores and the matrix gives us 1. Yes.
Yes.
Yes, you are right. Yes, you're right. Okay, so you can put here. Yes. So this is our in fact porosity 1 minus this one. Okay, you're right. And now, please provide other information to derived values. So right-click to derived values and global evaluation. Choose global evaluation. All right. And as an expression, click to expression in this empty yes and plus. Sorry, this plus in expression, this blue one. Yes, this one. And just choose definitions from component 1. And you have variables. And just choose flux AVG. Double click. And add plus, press plus again. choose variables and con_avg. All right, and press evaluate now. Okay. And go to the bottom of the table. All right. So you can see here what is the average concentration and what is the average flux. And put those values to the table I have provided in the guidelines together with the porosity. All right. One minus 0.55868. Yes, exactly. Yes. What is the diffusion coefficient in solid material here? So go to component to transport of diluted species. Yes, open this. This left triangle. Press left triangle. Transport of diluted species. You have left triangle near this. Yes, I can see it now. Okay, good. Click to transport properties. Probably there is some delay when I see the action. All right, and you have here this diffusion. Just go to the bottom to see the diffusion section. All right, and this diffusion is D2 here. Okay, so let's go to parameters now. In the model builder parameters on the top, model builder, not settings. Model builder window, left window. All right. Go to the top, parameters, and yes, and value D2. Yes, so 1 10 to minus 5 square meters per second. Just put this value to the table as the, you can copy it if you want, to the table. To the table in the guideline. I can see it. All right. Diffusion coefficient in solid material, not effective. This is in solid. All right. And put also average concentration and average flux. Just
the diffusion coefficient was present from the beginning, right?
What do you mean present from the beginning?
I mean, where did we get this value from? Is this like a default or an average value for solids, or?
No. It is because this procedure should not of calculation of effective diffusivity should not depend on the diffusion coefficient.
I see.
But of course, it's better to use value which is close to the material value. All right. All right. Okay, good. So how to calculate effective diffusion coefficient? If you show me the description of the effective diffusivity project, this one, yes. Go to the, I think, third page, something like that. Another one. Another one. All right, here. So if you just rearrange this expression here, the first one on top of the page. So effective diffusivity is average flux multiplied by L1 divided by C0 minus C out. C out is the average concentration. L1 is the length of the sample, and it is, as I remember, 2.5 micrometers. Do not forget to change unit to meters. And what is C0? Sorry? Oh, meters. Length in meters. Because everything COMSOL calculates in SI units, as you remember. So average flux multiplied by L1 and divide by the difference, C0 minus C out. C out is the value from the table. C0 is the value on the left boundary. So let's go back to COMSOL and let us see in the boundary we have concentration, boundary condition, transport of diluted species, we have concentration. Go to concentration, and this is Cmax. Let's go back to properties and see parameters and see how Cmax looks like. Cmax is 3 mole per cubic meter. So this is the value which you should provide. This is as C0. All right. And now use this formula, use those values, and calculate effective diffusion coefficient. You can do it in the table. This is why I provided this table. And if you have the values, you can calculate effective diffusion coefficient. Please do this now. Do this now. I'm waiting. Just do it outside the COMSOL. In COMSOL, you have to calculate all the data to the table. I think not all, because effective diffusivity will be calculated. You're right.